All right, welcome to Chapter 9. I've organized this by section. There's no general overview of 9 itself, but I'd like to do a general overview section by section. So this is section 9.1, and what's happening in here is we're going to have two proportions coming from two different populations, and we're going to compare them. And so the two things that we're going to do is test a hypothesis directly comparing two independent populations proportions. So what you'll notice is that the two populations are completely different from one another. There's no overlap. They're independent. And we're going to look at some percentages, some proportions, some rates that are in each one, and we're going to directly compare them. I bolded directly because the comparisons are always this one's bigger, this one's smaller, this one's not equal to, the two are equal. There's always just a direct comparison about their relationship. And so what's going to happen is they're going to give you a problem and ask you to test the hypothesis using the traditional method that we've been doing. And so nothing is going to change there. And then they're going to ask you to test it using a confidence interval. And we're going to use the confidence interval that's appropriate for that test. And so we're going to get some 7 reinforcement as well. So as you hear these two things, that we're going to be doing a hypothesis test and we're going to be doing a confidence interval, let's focus on them in the order that they're talked about, which is usually the order of how they're asked in the book. And so you know what's going to happen if you have a claim, right, that a hypothesis to test, and that is you're going to need to know a test statistic. So I need to share with you the test statistic formula. So the test statistic formula, when you have when you have a comparison between two percentages or proportions, is going to naturally have that P symbol in it. You're not going to be surprised that it's a Z, because that will match both your 7 and 8 experience. When there were claims about the proportion in 8, we use a Z score. And so same thing here. And so here is the test statistic formula that they would like you to use. It's going to be a little bit different than what's in the book, because the book has some redundancy in there because of the direct comparison. So it's going to be P1 hat minus P2 hat. Actually, I'll write it out exactly the way it is in the book. Minus P1, P2, all over the square root of P bar, Q bar, all over N1, plus P bar, Q bar, all over N2. So the reason for all this extra notation is because we're getting two independent population samples, and we are going to use the sample results to compare the two. And so we got to incorporate both of those, and this is what it looks like. If we were to erase all of the P2s, it would look exactly like it did in chapter 8. Now the weird thing is this P bar. It's not an average or anything like that. It's what they call the pooled estimate. And the pooled estimate says, hey, I don't care which population you're coming from. What was the overall percentage of people that were doing that thing? And so P-bar has a very specific formula. The successes for one, the successes for the other population, and then the two sample sizes that they were dealing with. That's it. And all of this is typed out on page 416 for you. It's actually the very first thing that they go into. There's no verbiage like we're talking about right now. They just said, hey, here it is, because you've done all this before. Obviously, Q bar is 1 minus P bar, so there's no special formula for that. The trick here, though, is you cannot round this. So this P bar, and this is definitely in terms of a workload, the worst of the 3 sections, because of this P bar. They'll model it for you. When they model it, they put P bar out to, and let me count. They have 8 decimal places of accuracy when they round it. It's up to you whether you want to round it or not, but if you do round it, you must keep at least 8 decimal places of accuracy. And the reason for that is the p-bar is involved in a square root. And when it's involved in a square root in a product, if you have rounded off values, they'll tend to get pretty far away from one another. So that is what we're going to do. And you're going to have the exact same thing. You'll know very well whether it's a one or two-tailed test. You'll know that if it's a greater than symbol, it's a right-tailed test. Right? And you're going to go get your z-value up on the right-hand side. You're going to take your significance level and put it into that one tail. The left is a less than, and then you remember that a not equal to from your chapter 8 experience is a two-tailed, right? Tail on each side. So if the significance level was 0.05, that right tail would have a 0.05 here. The left tail would have a 0.05 down here, and the two-tailed would have a 0.025, 0.025. So the other thing that we're going to do, if I scan back up here, is to find a confidence interval for the difference of the two proportions. So when you go to get your confidence interval, you're gonna need to get an error. And that error formula looks like this. It's z alpha over 2 square root of p1 hat q1 hat all over n1 plus p2 hat q2 hat all over n2. And that's also typed out on that 416, 417 page there. So all of this you probably have already read about it. And so this is the error formula that we're going to use. And confidence intervals are always for the difference. So we're going to get the difference of those. So it's going to pretty much be like this: x1 bar minus x2 bar plus or minus this error. And that will be a second way to test a hypothesis, and we'll show you how as we get to an example. So this is just the overview. So one of the crazy things is that this confidence interval needs to be appropriate to the hypothesis test. Remember that confidence intervals are always two tails. So if you had let's just play a what if game. Let's suppose part A was to test the claim that the percentage was greater than 75. Well, then you know your null hypothesis is P equals 75, and your alternative hypothesis is P is greater than 75, right? Just like it was before. Actually, it won't be that way. I apologize. I forgot what section we're doing. That's a chapter 8 problem. What you're going to have is that one of the probabilities, the percentage of, I said probabilities, but the percentage overall in 1 is greater than the percentage in 2. And so your null hypothesis will be P1 equals P2. And your alternative will be the same thing as the claim, because it can be. You know right now that this is a right-tailed test. And so if alpha is equal to 0.05, you put 0.05 there, you go look it up, and you get a 1.645 coming out there. Well, when you go to do part B is going to ask you to construct the confidence interval that is in accordance or corresponds to or is appropriate for the hypothesis test. Now, there's a reason why they want that worded that way. They want to make sure that you're using the exact same 1.645. And so remember, confidence intervals are two-tailed. And so if you have 0.05 here, then you have 0.05 here, and you're really dealing with the 90% confidence interval. So you're going to find the 90% confidence interval, and you're going to use the same 1.645 as your z alpha over 2 for that formula. So I don't know if this is going to make a whole lot of sense, this last discussion, until you actually see it applied in a problem, but I need to lay the groundwork for you. So all the problems are going to have an A and a B. The A is going to be to test it using the traditional method, and B is going to be to test the claim using a confidence interval, because the idea is to show you that the two are really the exact same thing. They're accomplishing the exact same thing. They're not the exact same thing. And so 9 will help point that out, as we've done in some of the Zoom sessions, in 8 if you've been able to attend those. So this is the general overview of 9.1, and what you'll see next is some problems being worked.